A little learning is a dangerous thing. A little learning may lead us to believe that we understand things way beyond our comprehension. Great learning is even more dangerous. Great learning opens the door to possibilities and choices, and with choices comes responsibility. Not always a character trait of the human race. No amount of learning is as dangerous and as destructive as ignorance. Certainly, information can be used for good or for evil, but so can ignorance, and ignorance leaves us blind. We are here to listen to the 2025 Nobel Lectures, 9 laureates of great learning, 9 dangerous men. It sounds like the title of a Western movie, doesn't it? I look forward to seeing them all riding off into the sunset to the music of the great master Ennio Morricone. Like the heroes of classical westerns, you are indeed armed and dangerous. Armed not with 6 shooters, but with great learning, ready to do battle with the ultimate dangers facing humanity. Disinformation, alternative truths, and chaos. Darkness is strong and will prevail in the absence of light, and while it takes only a single candle to light up the darkest room, a lone candle may easily go out. This is why science is important, but teaching is paramount. Working in research is to learn. Communicating research is to teach. Research without teaching is hiding your light under a bushel. Light should be shared. Gathering and multiplying light leads to enlightenment, and enlightenment, as opposed to mere light, is robust. When Alfred Nobel planned for the conferment of the prizes that bear his name, the Nobel Lectures were an integral part of them. In these times of war and climate crisis, when truth itself is under attack, we have more cause than ever to feel gratitude towards Alfred Nobel for his vision to celebrate knowledge, light, and enlightenment. Perfectly aligned with the greatest benefit to mankind, this year's prizes are indeed eminently useful. The prizes in physics and economic sciences celebrate how that which is useful and small can be grown large. The prize in chemistry goes one step further to reveal that there are uses of that which isn't even there. To our laureates in physics, chemistry, and economic sciences, I extend my heartfelt gratitude that you have braved the inconveniences of travel to come to this Ultima Thule at the very edge of the world, to bring light at a time when that is in short supply. Thank you for your willingness to teach. I also want to thank all of you here who have come to listen, in this hall and online, for your willingness to participate in Alfred Nobel's dream about enlightenment. Thank you for your willingness to learn. In the darkness of our Nordic winter, bring it on. Let there be light. Fiat lux. I now invite Ola Eriksson, Chair of the Nobel Committee for Physics, to introduce this year's laureates in physics.
Good morning, ladies and gentlemen. You are all accustomed to, in your everyday life, what you see on the screen behind me. On your left, you see a boy throwing a ball onto a wall and it bounces back. And you know in your everyday experience that the picture to the right just doesn't happen, not in the world of classical physics. The ball never ever goes through a forbidden region. In the microcosmos, that of atoms and electrons, this is everyday life experience, and there's no problem with this at all. Alpha decay from the atomic nucleus is one such example. In the early 1980s, late 70s, researchers started to think about if it is possible to also see the quantum mechanical tunneling that is so well known from the microcosmos, if that was also possible in the macrocosmos for macroscopical objects. And it was identified that the most suitable object to investigate such an effect in was that of electrons in a conductor forming a superconducting state. So in the top graph, you see electrons in a normal state in a normal conductor, copper wire, as an example. In the middle panel, you see the superconducting state where electrons pair up and they're holding hands. Those little spherical objects have now paired up into what is known as a Cooper pair. And at very low temperatures, they form a superconducting ground state, the Bose-Einstein condensate, that has no distinguishability between Cooper pairs. They are all in one big macroscopic object. So this was then investigated to investigate and see if the laws and the discoveries and the phenomena of quantum physics and quantum mechanics could also be seen in macroscopic objects. And a macroscopic object of this kind can be trapped into a potential well, and that's the figure you see on the right. You have the energy of the well on the y-axis, and you have the position on the x-axis. You can imagine this would be you hiking around in the Swedish mountains, and you're in a valley, and you want to come out of this valley, and you cannot tunnel through it. You have to hike above the peak. But in the world of superconducting macroscopic phenomena, this was not quite the case, and the tunneling phenomenon was discovered and described by this year's Laureates. And the smoking gun experiment that proved this, that proved the tunneling phenomenon, that is what you see on the left-hand side here. You see the escape rate of this object on the y-axis, and you see its position. That would be your position if you're hiking around in the Swedish mountains on the x-axis. Read to you the motivation to this year's Nobel Laureates: to John Clark, University of California, USA, Berkeley; Michel Devray, Yale University, University of California, USA, and Google Quantum AI; and John Martinez, University of California, and Quolab, USA, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. So please join me now in welcoming the first speaker of our trio of speakers to the stage to give his presentation. You want to sit down? Good.
From slugs to macroscopic quantum phenomena. I would like to talk about this subject in two separate episodes. The first is my work at the Cambridge University, where this was really the ultimate route why I ended up at UC Berkeley. So I will begin with an overview of the work I did many, many years ago at Berkeley. And I'm sorry, I will begin with talking about my work at Cambridge University, and then I will move on to talk about my research at UC Berkeley, which talks about three topics: macroscopic variable, energy level quantization, and macroscopic quantum tunneling. So let me start out by talking about my research at Cambridge. I was a graduate student at the Royal Society Modern Laboratory on Free School Lane in Cambridge, and there's a more recent photograph of me. My thesis advisor was Brian Pippard as of the 1st of October 1964, and he set me a rather tough project. He wanted me to be able to measure voltages as small as 10 to minus 12 or 10 to minus 13 volts at a time when the state of the art was 10 to minus 9 volts. Well, I pondered this for a while, and I thought that's going to be a difficult experiment. But a little bit later, Brian Josephson gave a colloquium explaining Josephson tunneling. And this really changed my world, and to be honest, the world of many other people. But he spent quite a lot of time talking about various topics, and one of the ones he talked about was flux quantization. And the basic idea there is that if you have a superconducting ring in which there is superconducting magnetic flux, then the flux is quantized in units of the flux quantum phi 0, which is equal to Planck's constant over 2e. Of course, he talked about Josephson tunneling, and the basic idea there is that you first of all deposit a thin film of superconductor on an insulating substrate. You then oxidize it, and then you deposit a second film, and that's the basic principle of the Josephson junction. But he went into this in considerably more detail, and on the top left-hand side here, whoops, we see an insulating barrier, which is, an insulating barrier which separates two superconductors, and the Cooper pairs, which are what makes superconductors superconducting, are able to tunnel through this barrier. And on the right-hand side, you see the plot from the very first observation experimentally of Josephson tunneling by Anderson Rowell at Bell Labs. And what you see on the vertical axis is the current versus the voltage on the horizontal axis. And at very low currents, no voltage appears, but as you increase the current sufficiently, then you get a transition to the voltage state. And this depends actually on the magnetic field that one is applying. Well, Brian Josephson worked out the two very short equations that explain all this, and they're written here. The first is the current I through the junction, and that's equal to I0 sine delta, where I0 is the maximum supercurrent, or the critical current, and delta is the phase difference across the barrier. In the voltage state, the delta by dt can be written as 2 pi times the voltage divided by the flux quantum. And he did this remarkably in his very first year as a graduate student at Cambridge. and he won the Nobel Prize in 1993. Another very important development that happened just 1 year later, in 1964, was by Jacob Lamb, Silver, and Mersereau, and they came up with the idea of the SQUID, the superconducting quantum interference device. And the basic idea is that you have a superconducting ring interrupted by two Josephson junctions. And remarkably, if you start to change the magnetic flux in the loop, then the critical current oscillates as a function of that flux, and the period is phi0, the flux quantum once again. So the SQUID unites the two ideas of Josephson tunneling and flux quantization. And this is on the right, a figure of the device that they made. And at the bottom, you see there's a superconducting film. And then on top of that, there's a rather thick layer of insulator. And then at each end of that is a Josephson junction. And the plots here are of the Josephson current versus the magnetic field. And if you look here, you see that as you change the magnetic field, there is these oscillations in the critical current. Well, the very next day, my thesis advisor, Brian Pippard, came into my office and he said, "John, how would you like a voltmeter with a resolution of 2 × 10⁻15 volts in 1 second?" And I thought, that would be amazing. But then he explained how you would do this. And here is what he drew on the blackboard. And on the right-hand side, you see a SQUID. And then the inductance of the loop is L, and it's coupled to another inductance with the same inductance L in series with a resistor, so that if you apply a voltage across this input circuit, then you couple flux into the SQUID. And just for simplicity, he said, let's make L equal to M. And basically, that's a digital voltmeter. And the voltage resolution is given by V input, which is equal to I phi0 times R, and that's the amount of current you have to apply to get one flux quantum in the loop. And if you choose a time constant of 1 second, then you find that the actual resolution is 2 × 10⁻15 volts. And that was quite remarkable at the time. It would represent a 6 order of magnitude improvement in the state of the art. However, there was a problem. The modern laboratory did not possess the equipment to deposit thin films. And so I couldn't make a device that replicated the kind of device that had been made in the US at the time. And I spent several weeks trying to fabricate a Josephson junction from pieces of niobium foil and niobium wire, sometimes soldered together with lead-tin solder, and none of my attempts was successful. Fortunately, my problem was solved one day during our daily tea break, when I was expressing my frustration at not being able to make a Josephson junction. And Paul Raitt, who I remember very well still, a fellow research student, pointed out that niobium has a surface oxide layer, and lead-tin solder is a superconducting wire. Why don't you put a blob of solder on a piece of niobium wire? And he was suggesting a device that looks like what's on the left-hand side here. And you can see that there is a niobium wire, and I've put a blob of solder on it, as you can see here. Then there are 2 leads so that we can measure the current voltage characteristics. And before dinner, and then I put the device in my cryostat with some liquid helium, and before dinner, that's what we saw. So once again, we have current on the vertical axis and voltage on the horizontal axis. And what you see is that at low currents, there is no voltage, and then when you increase the voltage sufficiently, then you have a voltage developed. So that was, for me, the beginning of how to make a Josephson junction. The day after, I put this device on my desk, and when Brian Piphard came in the morning, he said, "It looks as though a slug crawled through the window last night and expired on your desk." And so here's a photograph of a slug. So anyway, that decided the name of this device. And so the slug was the superconducting low inductance undulatory galvanometer. And so if you now look at this figure here, you find that the slug has an extraordinary property, that when you change the current flowing along the niobium wire, the voltage across the slug oscillates as a function of this bias current. So quite remarkably, the slug behaves as though it were a squid. And this enabled me to make an analog voltmeter with a voltage noise of 10 to the minus 14 volts per root hertz. And so this was still in my first few months of being a graduate student. So I spent a great deal of time after that trying to improve the slug, but also doing a variety of experiments that could only be done if you had a sensitivity of this kind. Well, after years went by, I started to ponder about what I should be doing next. And a little while before I graduated, Paul Richards, who at the time was a faculty member of the physics department at UC Berkeley, came to visit my lab. And he was curious to see what I was doing, and also I would like to hear what he was doing for his research. And I really enjoyed meeting him. So, as I said, I was pondering what to do next. It occurred to me that as a postdoctoral scholar, it will be a very interesting trip to the US to go to UC Berkeley, where Paul was a graduate student, was a faculty member. He was a wonderful mentor for me, and he and his family became my close friends. Very sadly, he's no longer with us. So on January the 6th, 1968, I moved to the physics department at the University of California as a postdoc for a year. And I worked away at my slugs again and various applications that you could do with them. And they then invited me to become a faculty member and also at the same time a senior scientist at Lawrence Berkeley National Laboratory. And then I started my research group. Sorry. I think I may need some help here.